Hello guys, today we'll be looking at one very important tool that we can use to differentiate complicated functions. This is known as the chain rule. Right, let me start off by reviewing the chain rule for functions of one variable. Suppose we have y equals f of x and x equals another single variable function, say g of t, where both f and g are differentiable functions. Then y is indirectly a differentiable function of t. Well, this is because we can write y equals f of g of t. So by means of composition, y is implicitly a function of t. Therefore, it makes sense to talk about the derivative of y with respect to t. Okay, so basically the chain rule says that we can compute this derivative dy dt by multiplying dy dx by dx dt. Well, as you can see on the right hand side, it looks as if we can cancel the dx to get the dy dt on the left hand side. Well, although we can remember chain rule in this way, strictly speaking, such cancellation is actually illegal because these guys are not fractions. Okay, as it turns out, there are many versions of chain rule for functions that depend on more than one variables. So we're going to look at those today. Let us start off with the simplest version of this. Alright, here's one version of the chain rule for a two-variable function. So suppose z equals f of xy, which is a differentiable function of x and y, where x and y are both differentiable functions of t given by g and h respectively. Then z is a differentiable function of t by means of composition, since we can write z equals f of g of t, comma h of t. So g is implicitly a single variable function of t. Therefore, it makes sense to talk about the derivative of z with respect to t. Right, in this case, the chain rule says that this derivative, dz dt, can be given by the partial derivative of f with respect to x times dx dt plus the partial derivative of f with respect to y times dy dt. Also notice here that we have used the normal d in the notation for the derivative of a single variable function. Right, so this is the chain rule. In this case, where our function f is a two-variable function of x and y, where x and y are single variable functions of t. Okay, here's one example of a two-variable function f given by x squared times e to the y, where both x and y are single variable functions of t. In particular, x equals t squared minus 1 and y equals sine t. So we want to find dz dt, which according to chain rule is equal to f sub x times dx dt plus f sub y times dy dt. So differentiating x squared e to the y with respect to x, we'll have f sub x equal to 2x times e to the y. Dx dt is the derivative of t squared minus 1, which is 2t. And likewise, f sub y is just e squared times e to the y. And finally, dy dt is the derivative of sine t, which is cosine t. Right, so we have arrived at an expression for dz dt. If we like, we can substitute for x and y in terms of t, but we can leave the answer in this form. Another version of chain rule is concerned with a two-variable functions f of xy, where both x and y are again a two-variable functions. So formally, suppose z equals f of xy is a differentiable function of x and y, where both x and y are some differentiable functions of two variables s and t respectively, then implicitly z is a two-variable function of s and t by means of composition, since we can write z equals f of g of st in place of x and h of st in place of y. So implicitly z is a function of s and t, therefore it makes sense to talk about the partial derivative dz ds as well as dz dt. Right, the chain rule in this case says that the partial derivative dz ds can be written as df dx times dx ds plus df dy times dy ds. Similarly, dz dt can be given by df dx times dx dt plus df dy times dy dt. So essentially we have two equations here, one for the partial derivative dz ds and the other one for dz dt. Alright, so as you can see in this case of our chain rule, there are three types of variables. First, we have the independent variables given by s and t. We also have the intermediate variables given by x and y. And on top of those, we have the dependent variable z. Right, a good way to remember chain rule is by means of a tree diagram. So as you can see in the picture, we have on top of this tree the dependent variable z, below which we have the intermediate variables x and y. And now as we move from the dependent variable z to the intermediate ones, x and y, along their respective branches, we write down the corresponding partial derivatives. For example, along the branch from z to x, we'll have the partial derivative dz dx. So repeating this procedure for all the other branches, including those that go from the intermediate variables to the independent ones, we eventually arrive at the tree diagram for the chain rule. Alright, here's how we remember chain rule by using a tree diagram. So for example, if we are interested in the partial derivative of our dependent variable z, let's say with respect to the independent variable s, then what we'll do is to look for all the branches that go from z to the independent variable s. In this case, we have two branches, one going down on the left hand side here, another one going down on the right hand side over here. So as we go along each branch, we'll pick up the corresponding partial derivatives and multiply them together. So for the first branch, we'll have the term dz dx times dx ds. And this will be added to the term given by the second branch, which is dz dy times dy ds. Okay, so likewise, we can write down the chain rule for dz dt by considering all the branches that go from z to t. Right, here's one example where we have a two-variable function given by z equals e to the x times sine y, where both x and y are some functions of s and t. So we can find the partial derivative dz ds and dz dt using the version of the chain rule we saw just now. Well, in particular, the partial derivative dz ds, according to the chain rule, is now the expression here on the right hand side, and after computing the corresponding partial derivatives and substitution, we'll arrive here at an expression in the second line. Actually, we can leave our answer as it is here in the second line without actually substituting for x and y. Okay, so this is the partial derivative with respect to s. Likewise, we also have an expression for dz dt using the chain rule. Right, in general, the chain rule can be extended to as many intermediate variables as we want, as well as any number of independent variables. For example, let's say we have a dependent variable u, which is assumed to be a differentiable function of n intermediate variables, let's say x1 up to xn, and each of these intermediate variable xj is again a differentiable function of, let's say, m independent variables t1 up to tm. Then our function u is implicitly a function of t1 up to tm. Therefore, according to the chain rule, we'll have an expression for each of these partial derivative, let's say du dti, which is given by a sum of partial derivatives that involve each of these intermediate variables. Perhaps it's easy to see one example in a general case. For example, here we want to write down the chain rule for the following function w, which is also identified as the function f of four variables x, y, z, t, where each of these x, y, z, t is a differentiable function of variables u and v. Alright, this is the tree diagram for our function. On top of this tree, we have the dependent variable w and the four intermediate variables in the middle and uv in the bottom of the tree. So for example, if we want to find the partial derivative of w with respect to u, then by using the four different branches that go from w to u, using the tree diagram, we'll be able to write down the expression for this partial derivative as given here on the right hand side. So basically, as we go down each branches, we pick up the corresponding partial derivatives and multiply them together, and that will give us an expression here on the right hand side. Okay, likewise, using the branches leading to the variable v, we'll get a chain rule expression for dw dv. In this example, we are given the equation w equals some function f of x squared minus y squared and y squared minus x squared, where this function f is assumed to be a differentiable function, so that we can apply chain rule. Perhaps what looks a bit strange is the way we write the function in this example. Actually, this is a lazy way of writing f of uv, where u represents the expression or the function x squared minus y squared and v equals y squared minus x squared. In other words, w is a function of intermediate variables u and v, where each of these u and v are functions of x and y. Okay, right, we're going to apply chain rule to verify the following equation. So let's first look at the tree diagram for this function. Well, since we have used u and v as our intermediate variables, we have w on top of the tree and u and v in the middle of the tree diagram and x and y in the bottom of this tree diagram. Therefore, implicitly, w is a function of x and y, so it makes sense to talk about the partial derivatives of w with respect to x and w with respect to y. Okay, so using this tree diagram, we are going to write down the various chain rule for the partial derivatives. So let us start with the one with respect to u, let's say. So we are making use of the branches going from w to to x. Right, as we go down the branches, for example, the first one here, we'll pick up the partial derivative. So here we have w sub u multiplied by du dx. Or you can write ux if you want. Maybe to be consistent, let's write ux. So we have wu times ux plus, according to the second branch now, wv times vx. We have no information about the function w, so we can't compute this, but we have information about u and v. So let's compute those. So ux is just the derivative of u respect to x, that is just 2x. We can't compute wv, but we can compute vx, which in this case equal to minus 2x. Okay, so by a similar argument, we can write down the expression for dw dy using the chain rule. This time it will be wu uy, which is minus 2y, plus wv times vy, which is 2y. So we have arrived at the expressions for our partial derivatives. Next, let's look at what we want to show. We want to show y times dw dx plus x times dw dy equals 0. So we need to do something to this expression. In particular, for the first one, we need to multiply by y. So we're going to do that. And for the second one, we're going to multiply by x. Right, doing this will give us the following expression, which we're going to write here on the next page. Y times dw dx. Let's see what happens if we multiply y to the right hand side. So we are going to get wu dot or times 2xy plus wv times minus 2xy. Likewise, for the second one, x times dw dy will become wu times minus 2x y plus wv times 2yx or 2xy. Finally, we are going to add them up. On the left hand side, we'll have the expression or the sum y times dw dx plus x dw dy. Now look at what happened to the right hand side. All the terms cancel out. So this one will cancel out with this one, and this guy will cancel out with this one. So we have 0. Hence we have shown the equation. Okay.